discuss flexibility matrix method. But before going to the flexibility matrix method, we should know what is the flexibility. Already we have discussed the stiffness. You know the stiffness, that is your force required for unit displacement. Okay. So if you have a relationship like this, okay, and if delta c with the displacement, and if this delta c is 1, okay, then we can see the force required for unit displacement with your stiffness. So here what we are doing, we are considering the axial element, and one end is fixed, other end is free. The length of this axial element is L, and we are applying force P at C, and due to this force, there is a displacement delta C. Displacement occurring at C, that is your delta C. Now, if this is your delta C, and if the length is here L, then we know strain, that is your delta L by L. So delta L is your delta C. So we can say the strain is your delta C by L. Again, we know the stress. We know that for Hooke's law, stress is proportional to strain, and we can write stress that is equal to E times epsilon. So we can write stress that is your E times epsilon at E times delta C by L. And we know the force that is equal to that force that is equal to area times the stress. If we do, we can get that area times area times the sigma, area times the stress. And if we put this value here, we'll get force P, that is your AE times delta C by L. And here this term we are writing as a K. So here we are writing E equal to K times delta C. Okay. Now here we say that force required for unit displacement is the stiffness. So here what we are doing, we are writing delta C in the denominator and writing that is equal to K. Okay. If this delta C is 1, then P will be K. Okay. If the delta C is 1, that means the force required will be equal to the stiffness. That is the definition of the force required for unit displacement, your stiffness. Okay. Now we know the flexibility that is equal to 1 by K. If F is the flexibility, then we can write F is equal to 1 by K. So if you write F is equal to 1 by K, then we'll get delta C by P. Okay, so flexibility is the displacement occurring due to the unit force. Okay, displacement occurring due to the unit force. Okay, so here we have learned that stiffness, that is your force required for unit displacement. Stiffness is the force required for unit displacement, and flexibility is the displacement occurring due to the unit force. Stiffness, that is your EA by L. Probably you can recall that in case of this matrix for a axial element, we obtain the matrix like this E A L, and here minus E A by L, here also minus E A by L and E A by L. So this was 1 1 and this was 2 1. Okay, 1 2 1 2. So K11 was the force required at 1 due to the displacement at 1, and K21 is your force developing at 2 due to unit displacement at 1. So here if you see K11, here we will get K11, and that value will get EA by L. And if we see the equilibrium conditions, okay, so here if we apply this force P, okay, that will be here P if your delta C is equal to 1. And if we apply load P here, obviously we'll get opposite force P here. Okay, so here we are writing this P as positive value. Here we will get minus P. Okay, and that value will be equal to E A by L, E A by L. Okay, and we are writing it minus sign. We are writing it that is your K1. Force developing at 2 due to the unit displacement at 1. So this way we get the stiffness matrix for axial element. Similarly, you can get the axial matrix for a truss element. Observe that in the case of flexibility matrix, the flexibility matrix will involve the term of your L by EA. In the stiffness matrix, we have the involvement of term EA by L. In the case of flexibility matrix, we will have the term that is your will have the term L by EA in the matrix. Next, we are going to see how you can obtain the flexibility matrix for a truss problem, for a beam problem, and for a frame problem.